and thermal. Okay? Mechanical energy, I told you, is the energy of what other M word? What's kind of like our clue? Mechanical energy is the energy of, Kayla? Motion. Very good. What are the two parts to mechanical energy? You add them together to get mechanical energy. Anna? Okay. What are you doing? Okay. Put it away. Thank you. What are the two parts of mechanical energy? You add them together to get mechanical. Very good. Kinetic and potential. Okay. Of those two, which is the energy where the action is being performed? Kinetic or potential? Kayla? Kinetic. Good. And then which of those is the energy where the action is being kind of built up? May not be happening yet, but it has the potential to later. Patty? Potential energy. Very good. Okay. So that's mechanical energy, kind of the energy of motion. Now, does it have to be when something's actually going from one place to the other? No. It could be when the object is just performing its action. Okay. For example, we talked about this one. Okay. Here's the kinetic, the action being performed. Here's the potential, correct? But nothing is moving necessarily. Okay. So that was mechanical energy. And then thermal energy, we just
I think it's because it was pointing up at you. I saw that. I know. Why is that arrow where?
There's a little arrow just sitting right here. Okay, anyway. What is thermal energy then? Think about that root word therm.
Oh, I thought.
Root word therm. What does it mean? Trinity? Heat. Okay. So thermal energy has to do with the blank of the matter. Bella? Very good. Temperature of the matter. Okay. So which one has less energy? An object of higher temperature, an object of lower temperature? Black? Has less energy? Lower temperature. Ooh, y'all all fell for that. Make sure you're listening. The lower energy is the lower temperature. Okay? The higher temperature it is, the more energy it has. Okay? So today we're going to talk about sound energy, which is a little bit more complicated. Okay? So the best way to understand sound, or to understand sound energy in the best way, we need to come up with need to add to our definition of energy. Yes, energy is the ability to do work. Okay? But to better understand sound energy, we need to kind of give it another definition as well. Okay? So, energy is anything that can cause change in a system. Energy, anything that can cause change in a system. Let me move my chair up here. Okay? So, in order for that to happen, it could be that you're doing work. It could be that you're moving something. It could be that you're turning something on. It could be that you're powering something up. But in this case, sound energy actually causes a change to the airwaves. Okay? To the actual waves in the air. It is produced from the vibrations that result after an object applies a force to another object. Those vibrations travel through the air as waves of energy. Okay? So, sound energy is all about vibrations. Okay? Whenever any sound is made, if I'm rubbing my hands together, it's producing vibrations. If you clap, it produces vibrations. If you snap, it produces vibrations. My voice produces vibrations. Okay? My voice is the result of my vocal cords in my body actually rubbing against each other. Okay? Put your hand like this. Now talk.
Hello.
Okay, stop. Stop. Do you feel the vibrations as you're talking? Okay? That is the sound waves traveling through your body and out of your mouth. Okay? Another example, put your fingers in your throat. Okay, stop. Okay, the reason why you don't feel vibrations as you whisper is a whisper is not a sound. Whisper is just air flowing through your esophagus and out of your mouth. Okay? A true whisper is not, your voice is not involved at all. It's just the sound of flowing air. Okay? Caleb, question? Anything that can cause change in a system. Yes, Bella?
I think it was Miss Rogers when she told us that Jesus knew quiet. I'm pretty sure it was her. She would say, if you can feel your throat vibrating, then you're being too loud.
Correct. Correct. It's a great way to remember it. Okay, so think about a drum, for example. Okay, if you hit a drum, okay, it vibrates, right? Raise your hand if you played drums before. Okay, good. Even if you've really banged on anything, you feel it vibrating. Okay, those vibrations. We're done. Those vibrations actually cause the air around it to move, kind of like a wave pool in a pool, right? When you jump up and down, it makes the waves of the pool kind of float, kind of oscillate back and forth. When vibrations happen, that causes the air around the two objects to oscillate or create waves. Okay, those vibrations or those sound waves are what travel to your ear as sound. Mm-hmm.
Yeah.
No. Connor? You might want to borrow one.
I literally have one right here.
Thank you, Nathan. Nathan, can he now borrow your notes to get the ones he's missed so far? Connor, you owe him a hug later. Actually, don't hug him. Give him a high five.
No, an elbow. No, give him a elbow. Coronavirus.
All right. Moving on. Okay. When the sound waves are gathered into your ear, they pass through the outer ear. Okay, which is where your ear canal is. This is the part you clean with a Q-tip. Okay. Your outer ear is the part that you actually you can see. It's right here. Okay. Which, by the way, is why it's all curved around the hole. Okay. All the little waves of your ear are shaped to help funnel all those sound waves into your ear. Okay. If you actually cup your hand around your ear and kind of bend it forward a little bit, you can funnel more sound waves into your ear, making it louder. Okay. Go now. Talk.
Subscribe to my channel.
Okay. Now keep talking, but remove your hand.
Subscribe to my
Keep talking, remove your hand. Now put it back. Keep talking.
I only have 9 subscribers. Talking.
Okay, stop. Did you hear the difference? Okay. When you kind of cup your hand around your ear and funnel more sound waves in, it gets louder. Okay. But as you just leave your ears alone, it gets a little bit softer. Okay. So your ear is shaped this way with circles kind of surrounding this hole to help funnel the waves into your ear. Okay. So the sound waves are gathered with the outer ear and shoved into the inner ear. Okay. Then they hit the eardrum. Your eardrum is right here. Your eardrum is actually it's a membrane. It literally is like a drum that has a covering over it. Okay. Anna, if you keep talking, I'm going to give you a warning. This little membrane right here is called a tympanic membrane. Okay? As the sound waves travel in, they vibrate that tympanic membrane like a drum, literally. Okay? As they vibrate, the bones on the other side, okay, there's 3 bones, the hammer, anvil, and stirrup. Okay? These are the 3 tiniest bones in your body, by the way. But inside the tympanic membrane, these bones, as the membrane shakes back and forth, it shakes those bones. Okay? The bones, as they shake, they bump up against your cochlea, okay? Which this is kind of like a water balloon almost. If I had a long water balloon and I tapped one side of it, Would Parker be able to feel the vibrations if he was holding it? Yes. The vibrations travel through the water balloon and he begins to feel that I'm shaking it, right? Same thing with your cochlea. As the hammer bangs up against the cochlea, your cochlea translates those vibrations to an organ of Corti over here, which passes the information to your brain. And your brain registers that as sound. Okay? Now, throughout your whole life, as you've been hearing sounds, your brain remembers what certain sounds sound like. For example, if I put you in a room and blindfolded you with 100 different women, you would be able to pick out which one was your mom based on the sound of her voice. Okay? Because you have grown up hearing your mom's voice. Okay? And your brain is trained to pick that out. All right? When I clap, your brain registers that as, oh, she's clapping, because your whole life you have been getting used to that sound. Does that make sense? Okay? So your brain is what translates those vibrations as certain objects, certain things. Okay? No questions right now. Actually, here, let's do this video first. How hearing works. What? Okay, you're gonna have to wait. Are you caught up in the notes now?
Yes.
Okay, then wait.
The ear has three parts: the outer ear or auricle, the middle ear, and the inner ear. The auricle,
Hold on.
the visible part of the ear, collects sound waves and directs them to the auditory canal.
Okay, so it kind of funnels them in.
Ear canal is lined with cilia and ceruminous glands. Earwax from the ceruminous gland and the cilia protect the ear from entry by foreign matter.
Okay. Your earwax in your ear functions very similar to the mucus in your nose. Okay? Mucus in your nose helps trap dirt and dust and foreign particles. As you breathe them in, it traps them here so they don't get into your lungs. Okay? If you didn't have mucus, you would get sick a lot more. You get a lot more junk into your body. Okay? Your earwax works the same way. It keeps dust, foreign particles, and dirt from getting into your ear and causing infection. Okay?
The thin tympanic membrane separates the outer ear from the middle ear. Sound waves cause it to vibrate.
Okay. Do you see how when the drum or the membrane kind of vibrates back and forth, it moves the three bones back there? Yes? Okay. As this begins to shake, it shakes the bones well because they're all connected.
Three tiny bones of the middle ear are the hammer, or malleus, anvil, or incus, and stapes, or stirrup. These bones pick up the vibrations from the tympanic membrane and transmit them to the inner ear. The Eustachian tube of the middle ear opens into the pharynx and permits air pressure to pass between the ear and the outside air.
Okay. Raise your hand if you've ever had an ear infection. Or if you've ever had strep throat or a cold and it makes your ears hurt. Okay, this is why. Your Eustachian tubes right here, they actually connect all the way down from your ear, okay? And they connect down here to your throat, okay? So if you're having a lot of drainage or something and you have a cold, sometimes it can make your ears kind of itchy, okay? Or it can make your ears hurt. If you have an ear infection, I'm pretty sure it has to do with the fact that your Eustachian tubes get swollen and inflamed, and you start kind of trapping mucus in there, or like just sinus fluid in there, and it gets infected. Okay, that's why it makes your ears hurt. All right, or that's why a sinus cold or a strep throat can make your ears hurt as well. If you know someone who had to have tubes put in when they were a little kid, usually that means that their Eustachian tubes weren't developed properly, so they were getting ear infection after ear infection after ear infection. Okay, and they had to go in and surgically implant better tubes in there to help kind of keep this open and clear and the pressure to equalize on both sides. Does that make sense? Okay. All your cavities, the holes in your head are all connected. Your nose, your throat, your ears, everything. Make sense? Bella?
Well, that's what my mom says not to like sniff and like if you like if you have a burgers and you like sniff it's really hard and it's really bad because
Yeah, I guess it could cause a lot of pressure in there.
yeah, it's happened to me before. And two, how come like last night I realized well I realized this before but I remembered that when I was laying down, like I heard this thumping, like my ear was closed like this. And
You heard this thumping?
yeah.
You're probably hearing your heartbeat. You're hearing the blood pumping through. Yes.
So actually, some of the questions are what happens like
Ringing in your ear. Someone in the last class asked if they were telling us that ringing in your ear is because there's just kind of like sound waves that are still bouncing around in your ear, and they're just kind of continually bouncing in there. I really don't know what it's from, to be honest. So I can't really answer that, but that was what they said. So maybe that's what it is. All right, let's finish this, and then we'll do more questions later.
The inner ear is maze-like, consisting of bony and membranous structures surrounded by fluid. The semicircular canals are fluid-filled bony loops that help maintain our body's balance. The cochlea is a fluid-filled.
Okay. So, also, your cochlea, the organ on the very inside of your ear, is filled with fluid. That's why if you have an ear infection or strep throat or something, sometimes you can get kind of dizzy, okay? Because if your fluid in there, if it gets off, like it's too much or too little, you can lose your balance. That fluid is what keeps you kind of helps you kind of even out. Does that make sense?
Snail-shaped structure that houses the organ of corti, true organ of hearing. The fluid aids in the transmission of the vibrations. The organ of corti changes the vibrations.
So this is like the water balloon I was explaining. Okay, as it hits that fluid-filled kind of balloon, almost the cochlea, it transmits the vibrations to the brain.
Into nerve impulses that are picked up by the auditory nerve. Sound waves are collected by the auricle, or outer ear, and sent to the auditory canal, tympanic membrane, ear bones, and then to the cochlea, where the vibrations are changed by the organ of corti to nerve impulses and transmitted by the auditory or cochlear nerve, the temporal lobe of the brain, for interpretation.
Okay, so last one with the cochlea. My first year teaching, I had a student who I don't know, I can't remember if it was like her cochlea wasn't developed properly or maybe she didn't have one. I really don't remember. But basically she was born without a proper cochlea. Okay? So everything else worked fine. The sound waves would go in, the hammer would beat against it, but there was nothing for it to vibrate and therefore send the vibrations to her brain. She couldn't hear anything. Okay? So when she was a young child, they did a cochlear implant. They surgically kind of implanted, I don't know if they put cochlea in or if they put a machine in there that would vibrate. I don't know. But she had a hearing aid that she wore, and then she had a Bluetooth microphone, basically. Okay. And so when I was teaching her, I would wear a microphone so that it would pick up my voice and kind of translate the vibrations to her ear a little better because her ear wasn't quite as strong as everybody else's. Does that make sense? So she had a cochlear implant because that organ wasn't developed properly. Bella?
So was she deaf?
She would have been without the implant. So with that, I don't know if she was still considered deaf, but with that she was able to hear me. Yes.
So about like hearing things, it's so annoying because when I'm trying to like go to sleep, my brain like generates these like sounds. Sometimes they're like creepy. And
Keeps
like,
you up?
Yeah, I cannot fall asleep. I cannot tell if it or like what's an actual sound or what's like something that's coming from my brain.
Mm-hmm. Yeah. Caleb?
So I have a really good question.
Okay.
Whenever you're like thinking of a thought, you can like do something with it, but not actually do it. But you've never heard it before, also. Yeah,
I'm confused. Yeah, I don't know.
like you're just thinking of a random sound in your head that you've never heard of.
You're thinking of a random sound in your head that you've never heard of?
Like,
Then you're probably imagining how it would sound.
How do you hear that sound? Yeah, because no sound is coming.
You're not actually hearing it, but your brain is telling you what it would sound like. But you're not actually getting sound into your ear.
In a way, you're thinking that your brain is registering the sound.
But your brain. I wonder if it's like you're kind of asking a very complex question, but it's kind of like your memory is creating something in your like subconscious that you're kind of imagining how it would sound, even though you've never heard it. Does that make sense? Okay. All right, one more or two more, and then we're gonna go on. Trinity and then Nathan. Trinity. So if you just cut all this cartilage part off and had just a hole right here, you would still be able to hear because all your organs are still working. I'm assuming you would not be able to hear as well, and you would not be able to hear as much because you wouldn't have this kind of like megaphone structure almost kind of funneling the sound waves in. That's my thought. Nathan?
Because in the video it said that the earwax kind of like easier like this the wall.
Mhm.
And then how come when I had an ear infection, why did they have to take all the earwax out? It's definitely not like I had too much.
Yes. So if you have too much earwax buildup in here, it can cause things to get trapped in there and then cause infection. Does that make sense? So yes, you want to have your earwax so that it keeps things from like getting into your ear. But if you have too much of it, it's like having almost like swelling in your ear. Does that make sense? Then it actually traps the dirt in there and it causes the infection. Does that make sense? Okay. Now, talking about the actual waves of energy. Okay, so that's how sound or how hearing works, how sound waves travel. But according to the different wavelength of the sound wave, you can have different sounds. Okay? Now, for example, a lower pitched sound, so something like is still producing waves. Is still producing waves, but the waves are much further apart. Okay? Kind of like this. You hear that, right? A little bit. But there's such long waves that you can't hear a whole lot of sound. But if I went like this, that's a lot faster waves, right? And you're hearing more sound. A higher pitch like this, the wavelength is much shorter and they're closer together. Okay? So, let me show you how to prove that. I think there's an ad on this one though.
Hello boys and girls and welcome to Hoopla Kids Lab, making science super fun and super simple. Today we're going to show you how to see sound. Now this is a really simple experiment and one that you can do with everyday objects around the house. What you're going to need is some cling film, hundreds and thousands, scissors, and a bowl and plate. What you need to do is get a good length of cling film and stretch it over the top of the bowl. What you're trying to do is make a sort of drum, where the cling film is the skin of the drum. And of course, just like a drum, you need to make sure that the surface of the cling film is stretched nice and tightly across the top of the bowl. When you've done that, get your hundreds and thousands, make a small indent with the tip of a finger, and sprinkle them onto the top of the cling film.
British something, I guess they call them hundreds and thousands.
And then if you try to talk directly into the cling film, you'll find that the vibrations from your voice make the hundreds and thousands dance around by themselves. If you think it's just my breath making them move, look what happens when I hum.
Put your hand like this and hum. Not that much. There's not much air, not enough to blow those around. All right, stop.
See?
Now watch the higher pitch. Okay. The higher pitched sound. The higher pitched sound has much shorter, faster wavelengths, which cause the sprinkles to jump around like crazy. Okay? This is also why, if you've ever seen, Anna, pick your head up, in videos or read in books or maybe even seen in real life, at certain pitches and certain volume of sound, it can shatter glass. Okay? That's why sometimes in like videos and things, it's the opera singer that's singing a really high pitch, it can cause the glass to shatter. Okay? That really can happen because if you're sending sound waves out at a certain frequency and the waves are moving fast enough, it can actually cause the glass to break. Okay? Because the waves actually just, they travel so fast it shatters the glass. Okay? So, my next question then, stop. My next question then is, okay, if sound produces energy and it produces waves, then why don't we use it to power objects? We use everything else. We use light. Think of solar energy, right? We use light from the sun to create electricity. We use thermal energy to create electricity sometimes with geothermal energy. We use mechanical energy, right? A hand-powered generator, things like that. But why do we not use sound? And this is why. Compared to all the other forms of energy, sound produces such a low level of energy that we don't use it for electricity. It could, but it would take so much sound, okay, to create just a little bit of electricity that it's really not practical, okay? The other kinds produce a little more electricity than the others. It's similar to how we talked about green energy and fossil fuels, right? We can burn just a little bit of fossil fuels to get this much electricity, or we can use this much green energy to get this much electricity. You remember how we talked about that? It has to do with efficiency. Which one produces the most for the amount that you have? And sound does not produce very much electricity. All right? So, last thing we're going to talk about is how is sound energy different from light energy? Okay? This is pretty fascinating. Sound waves must travel through something. Okay? If sound waves are literally waves of energy, there has to be something for the sound to create the waves out of. Okay? Whether it be air, whether it be water, whether it be, actually, I guess it's those two things, air or water. Okay? Light waves, however, do not have to travel through something. Okay? Think about space, for example. In space, there is no air, right? It's a vacuum. It's just emptiness. But light still travels through space. However, sound does not travel through space. Okay? If you were in space and you saw an explosion, you would see the light, but you would not hear it. You would not hear the explosion because even though the object explodes, there is nothing for that sound to create waves out of travel to your ears. It's just emptiness. It can't create waves with nothing. Does that make sense? Okay. So, sound does not travel through space, but light does. Sound is also kinetic energy. Okay, an energy of motion, while light is electromagnetic energy. Okay, so in your notes where it says how is sound different than light, you write the first bullet point here. Okay, you have a lot of lines there, right? Sound waves must travel through something, but light waves do not have to. That's really what you write. So I guess the first two sentences. Sound waves must travel through something. Can you read it? But light waves do not have to. That's the main difference. The sound waves have to have something to create the vibrations out of. Either air or water or something like that. Okay? Parker, question.
Like the sound waves, when they reach your ear and like vibrate your eardrums, how does the sound waves, or how do the sound waves, like, are they big? Because, like, how do they reach every single one of our ears?
Because they continue, yes. I mean, they're big, and they keep going for a long time.
So are they, like, wide too?
Not necessarily wide. Okay, but I'm sending, it's not just one single sound wave. I'm sending out multiple sound waves. Does that make sense?
So
Kind of like light. Light is a bunch of waves at one time, right? Kind of like that.
So would like a sound that you make with your voice, would that be like a combination of a bunch of different pitches?
It's either a combination of pitches or it's all. So I'm talking at this particular sound and it's coming out at all the sounding the same. That I'm talking that particular pitch, all the waves coming out are the exact same size. But if I talk at a low pitch and then you talk at a high pitch, now we have two different size waves traveling through the same room. Does that make sense? Connor?
I think the last two for thermal energy.
Okay. Can you look off someone near you? Reagan?
So of course, how sound travels, we're able to hear it. But it has to travel very fast if we're able to hear each other and as well see each other, like be able to sometimes read lips. So it has to travel like, I don't know, a very small fraction of a second so it can reach ours and match what we're saying.
Correct. It does travel fast, just not as fast as light. Okay? All right, that's the end of the notes, correct?
Yes.
All right, let me stop this recording, and then I'll take like maybe one or two more, and I'm going to give you the